Hello students, in today's class of electric current part 5, you are going to learn about Kirchhoff laws. History of Kirchhoff law. Gustav Robert Kirchhoff is a German physicist. He has described the various components of a circuit in just two laws, and these two laws had become the central part in the study of electrical engineering in 1845. He has proposed these laws in the year 1845. These two laws were generalized from the work of George Ohm, after whom Ohm's law was named. And these two laws can also be derived from Maxwell's equation. And these Maxwell's equations were related to the study of light, electricity and electromagnetism. But these were developed prior to Maxwell. Means Kirchhoff had proposed these laws prior to Maxwell's work. Now, introduction of Kirchhoff laws. What are these Kirchhoff laws? A pair of laws stating general restrictions on the current and voltage in an electrical circuit. So here, Kirchhoff laws are a pair of laws, means two laws. And these two laws were restricted to general restrictions of current and voltage in an electrical circuit. Then, what are these laws and how can we know about them? The first of this law states that any given instant, at any given instant, the sum of the voltages around any closed path or loop in the network is zero. What does the first law states is, at any given instant, means at any point in the circuit, the sum of voltages around any closed path. This closed path of the circuit is also known as loop. So, the sum of voltages around any closed path in the network, means that is in the circuit, is always equal to 0. And what does the second law states? The second law states that at any junction of paths, here the first law is about the complete loop, whereas the second law is about at any junction of path or node. The junction of the path can also be named as a node. So, the second law states that at any junction of paths or nodes in a network, the sum of the currents arriving at any instant is equal to the sum of the currents flowing away. So, in a circuit, when you imagine a junction, means a point where the components are meeting, that point is known as a junction. So, at the junction, the sum of the currents arriving at any instant is equal to the sum of the currents flowing away. So this is the second law. Let's go in detail. So these Kirchhoff laws are of two types. First one is Kirchhoff voltage law. I told that Kirchhoff laws are two laws and the first law is about voltage. So it is named as Kirchhoff voltage law. In short, it is known as KVL. And the second one is Kirchhoff current law, which is represented as KCL. Okay. The first law is Kirchhoff voltage law and the second law is Kirchhoff's current law. Okay. So here in this module you are going to learn about these two laws. Let's see the first one, Kirchhoff voltage law. So you are going to learn about introduction of the first law, then mesh analysis and exercise of it. Let's see. The introduction of the Kirchhoff's voltage law. What does this law states is, it is one of the fundamental laws in electrical engineering. The other being Kirchhoff's current law. So here I told you already that Kirchhoff's current law and Kirchhoff voltage law are related to the electric current. So this first law is one of the two fundamental laws in electrical engineering. That is, when you go to engineering or when you're studying about electricity and electrical works and all. So that study, in the study, this Kirchhoff voltage law is the fundamental law. And the other one is Kirchhoff's current law. So these two laws are the fundamental laws of electrical engineering. So Kirchhoff voltage law is a fundamental law, as fundamental as conservation of energy in mechanics. As we are knowing very well about conservation of energy, that is, amount of energy is always conserved, means it always remains constant. It can only change its form, but it does not lose anywhere. So here the same thing is applicable here. So Kirchhoff voltage law is a fundamental law, and this is based on conservation of energy. The next one is Kirchhoff voltage law and Kirchhoff current law are the starting point for analysis of any circuit. When you are trying to learn about any circuit, these two laws are the starting points to analyze about any circuit. Next one, KCL and KVL, that is Kirchhoff's current law and Kirchhoff voltage law, always hold and are usually the most useful piece of information. So here these two laws are always useful part which gives the information that you have to know about a circuit. Now let's see with the Kirchhoff's voltage law. This law in short is represented as KVL. This is also known as Loops law. And what does this law states? Let's see. This law states that the algebraic sum of the voltages across any set of branches in a closed loop is equal to 0. That is, the sum of voltages across any number of branches is equal to 0. Here the symbol sigma denotes the sum of all the voltages. V is written. This is the symbol of sigma which you have learnt already in maths. So here this symbol denotes that it is a sum of V, that is voltages, across any number of branches in a circuit is equal to 0. So what does the Kirchhoff voltage law says? It states that the algebraic sum of voltages across any set of branches in a closed loop, in any closed loop, the algebraic sum of the voltages is equal to 0. Let's see what it is. So here there is a circuit which contains a single loop, means a closed circuit which is only one closed circuit. Because later on you will be learning about complex circuit, whereas this one is a simple single closed loop circuit. And for this circuit, the KVL computation, means Kirchhoff's voltage law computation calculation, that is, it can be expressed graphically in that voltages around a loop are summed up by traversing around the loop. So how can we calculate the voltage across this loop? Is by moving around the loop. We need not move, means our imagination should move. That is, our imagination should be how the current is moving around the loop. So this has to be done. Now let's get into the details of it. Before going to the calculation, you must know the basics of imagination, how it has to be done when you assess a circuit. This first point states that the KVL equation is obtained by traversing a circuit loop in either direction, means you can start moving either from right to left or from left to right, or from top to bottom or bottom to top. You can go in any way. And writing down, after moving around, when you're moving, you should assess the voltage and the current, how it is moving. So here voltage at any point you should know how much it possesses at that point, and the current how much it is moving. Then after assessing, you have to write down those values. Write down the unchanged voltage of each element whose positive terminal is entered first. So here you have to start. When you are starting, it's a positive terminal entering first is taken as a positive, and writing down the negative of every element's voltage where the minus sign is first met. Means for the elements or for the components of the circuit which is reaching the negative terminal of the battery should be considered as negative. The loop must start and end at the same point. So when we are speaking that it's a loop means it is a closed circle. So it should start and end at the same point. And it does not matter where you start on the loop. You can start at any point on the loop, but you should come back to the same point from where you have started. So this you have to remember. Then the other point which you have to know is, note that a current direction must have been assumed. So when you are traversing, means when you are moving around the loop, you should imagine the direction of the current. The assumed current creates a voltage across each resistor. So when the current is moving, it creates a voltage. Means here current is moving means charge is moving. So when the charge is moving, it creates a potential at any point. So you have to imagine that the current which is moving here in the loop is creating voltage across each resistor and fixes the position of the positive and negative signs. So here when you are coming in the loop, when you come across a resistor, you have to able to assess whether it possesses positive charge or negative charge, because when the current is moving in the direction, and if you are also moving in the same direction, it possesses immediately the positive sign. But when you come across a resistor is a component which objects the flow of charge. So here the voltage at the point of resistor decreases, so it gets the negative sign there. And the next one says that the assumed current direction and polarity of the voltage across each resistor must be in agreement with the passive sign convention for KVL analysis to work. So here the current direction which you are considering and the voltage which is there at a point across each resistor at any point of the resistor, it should be in agreement with the passive sign convention of the KVL. What is that? KVL says that algebraic sum of the voltages is equal to 0. So it should obey that. The voltages in the loop must be summed in either direction, that is from the top to bottom or bottom to top or left to right or right to left. In any way it can be done. It makes no difference except to change all the signs in the resulting equation. So it doesn't make, except there is a change in the symbol, whether it is plus or minus, that's it. So this is about mathematically speaking. Strictly mathematically speaking, it's as if the KVL equation is multiplied by -1. So when you are taking in either direction, right to left or left to right, it is just the equation which is multiplied by -1. When you compare the two equations, it's like similar, except it is like it is multiplied by -1. Let's see what it is. Now let's see the summation of voltage in a loop. This can be done in any direction. Now let's see the first one. Here in this loop, the direction of current is from the positive terminal to the negative terminal. Imagine that even you are also moving in the same direction. Since both the directions are same, the potential at any point at the point is equal to the positive sign convention. So here the potential at R1 is equal to VR1 plus VR1, whereas at R2 it is equal to VR2. And as you move forward, the potential at the point R3 is equal to VR3, since both the directions are same. And when you reach the point, that is at the battery negative terminal here, the potential at this point is increasing here, since you are reaching the point of battery. So here the potential at this point increases, whereas you have reached the negative terminal. So it is in opposite direction and the sign convention is minus. So the potential at this point is -10. And the resulting KVL equation is VR1 plus VR2 plus VR3 minus 10V is equal to 0. Since the sum of voltage, algebraic sum of voltages in a loop is equal to 0. Okay. Now let's see the second one. That is, the direction of traversal is opposite to the first one. Now if you observe closely, the direction of current in the second loop is also the same as the first one. That is, from positive terminal to the negative terminal. But the direction in which our movement is opposite to the first one. That is, we are moving backward. Now here, since we are moving backward and the current flow is forward, the potential at this point R3 is equal to minus VR3, and it continues the same at this point. That is, the potential at R2 is equal to minus VR2, and the potential at the point R1 is equal to minus VR1, since the direction of ours is different from the direction of flow of current. But when you reach the point of the battery, here the potential increases, and here since the potential is increasing, it is equal to the positive sign convention, and its value is plus 10V, and the resulting KVL equation is minus VR1 minus VR2 minus VR3 plus 10 is equal to 0. So here in this situation, the assumed current direction is the same, that is from positive terminal to the negative terminal. But only one difference is that the equation is multiplied with minus 1. Just if you observe both the resulting equations, the second one is multiplied as if it is like multiplied with the minus 1. Since we have our imagination of movement is in opposite direction to the flow of current. So here the summation of voltage is done by moving in any either direction. So from this you must have understood that assuming the current direction fixes the voltage reference. Means when you imagine the direction of current, it helps us for the direction of voltage. Okay students, you have reached now the level mesh analysis. What it is? Analysis using KVL helps us to solve for the currents around each closed loop of the network, and hence determine the currents through and voltage across each elements of the network. So what is this mesh analysis is? Analysis using KVL, that is Kirchhoff voltage law, helps us to solve for the current, means helps us to find out the current where around each closed loop of the network we can find the value of the current for each closed loop, and hence we can determine the currents throughout the circuit or throughout the network, and voltage across each elements of the network also can be done. Now let's see what is the mesh analysis procedure. The procedure is that it has to undergo 3 steps. The first step is assign a distinct current to each closed loop. First, when you see a network, you have to identify the closed loop, and for that loop you have to assign the direction of current. Then step 2 is to apply KVL law, that is the algebraic sum of the voltages in the closed loop is equal to 0. That's what we have seen in the previous slide. The step 3 is that solve the resulting simultaneous linear equations, as you have seen first one and the second one, KVL equations. So when you solve those equations, you can get the required quantity, that is current can be calculated. So did you all understand the 3 steps? Mesh analysis involves 3 steps. First step is to assign a distinct current to each closed loop of the network. When you are given a network, in that you have to identify each closed loop, and to each loop assign distinct current. Then apply KVL law to it, and then solve the simultaneous linear equations. So in a network it can be 2 loops or 3 loops. As per the number of loops, you will be getting the number of equations. Suppose if you are seen in the previous slide, there is only single loop, so you have got only one equation. But if in a network there are 2 loops, you will be getting two equations. Then when you solve these two equations, you will be getting the values of the current and voltage. So remember that this mesh analysis involves 3 steps and it helps us to solve the values of current. So it's repeated the same very clearly. That is to assign a distinct current to each loop and then apply KVL and then solving those equations. For example, here if you see, here this is the network and in this network you can see the loops. First loop if you take the complete network, that is starting from A, B to F, E and A. So it's a starting complete one. Starting with A, we are moving right side and then downwards and left side and then towards up. So here this is one closed loop, and in this again, in this network there are two loops here. That is, the first loop is starting with A to B, D and C. Again from C to A. So this closes the loop. So loop means starting point and the ending point should be the same. Then only we say that it is a loop. So the first loop is A, B, D, C, A. Or else you can go in a reverse direction. That is A, C, D, B, A again. So this is also one closed loop. Now the other loop starting with C. So it can be C, D, F, E, C, or else it can be C, E, F, D, C. This is another, means the direction is different here, but the loop is the same. So here when you see there are two loops, the first one and the second one, A, B, D, C, A, C, D, F, E, C. So these are the two loops which are present here. Now let us apply Loops law to the circuit. So for the loop A, C, D, B, A. So this loop, when I take this first loop starting from A to C, D, B and A. So this is one loop, and in this loop let's apply the Loops law, that is summation of voltages. So here when I start moving from A to C, because my loop is which I have considered is A, C, D, B, A. So I start from A to C. So here when I am moving here A to C, when I reach the point here to this C point, the flow of direction is from this battery from the positive terminal towards the negative. From the positive terminal it had started, and the direction of current is shown in the arrow mark here like this. So the direction of our movement and the direction of current at this point is opposite. So the sign convention for the voltage at this point is taken as negative. That's why it is taken as minus V2. But as we move forward to this point at the point R2, here what happens? The resistance at this, due to the resistor R2, the potential at this point is decreasing. As it is decreasing, it is denoted by the negative sign. But our direction is also negative. So minus into minus it becomes plus. And the voltage at this point is plus I2 R2. I repeat it again. We are moving in the opposite direction of the current. So the direction is negative here. But the potential at this point decreases here. Due to this decrease in the potential at this point is considered as negative, and minus into minus is positive. So the potential at this point is plus I2 R2. And as we move forward, that is towards B, then from B to R3, again the potential varies here due to resistor R1, and here the direction of ours is same, opposite to the direction of current, so it is negative. and the voltage at this point is minus I1 R1. And as you reach this point, again the voltage increases here. So due to this increase, it is taken as positive. So here for the loop, first loop ACDBA, the voltage is minus V2 plus I2R2 minus I1R1 plus V1 is equal to 0. Now let's see the second loop, that is EFDC. So when you take the loop EFDCE, here the direction of current is from the positive terminal to this side. So here it is moving right side, and even we have also started moving in the same way. But here the problem is that when you are moving forward, the voltage at this point drops down. So due to it, its sign convention is negative. Since V is equal to IR, as we know from the Ohm's law, so potential at this point is equal to I1 plus I2. The current is at I1 plus I2, and R3 is the resistance here. So the potential at this point V is equal to IR. As we know, V is equal to IR. I is I1 plus I2. But since the resistance at this point is in opposite direction, drops down, it is negative. So potential is minus of I1 plus I2 into R3. Then as you move forward from F to D, and here the same thing happens, the resistance drops down here and the voltage becomes minus I2 R2, because in this line the current is I2. So here it is equal to minus I2 R2, and after reaching this point the potential increases. So it is equal to plus V2, and summation of voltage is equal to minus of I1 plus I2 into R3 minus I2 R2 plus V2 is equal to 0. This is in the bottom loop. Now when you consider the whole network, that is EFBAE, this loop when you consider, then the value of current in this loop starting from E is equal to, current is I1 plus I2 and it is towards R3. As the resistance is the objection of flow of current, voltage drops down here, so it is taken as a negative. So it is equal to, potential at this point is equal to minus of I1 plus I2 into R3. And as you move forward here, the potential continues, and at this point it still further drops down. So it is equal to minus, and the potential at this point is minus I1 R1. And after reaching this point, the potential increases. Since we have reached the battery, the potential increases. So the sign convention is plus here. So for this loop EFBAE, the voltage is equal to minus of I1 plus I2 into R3 minus I1 R1 plus V1 is equal to 0. So this is the Kirchhoff voltage law, and when you solve these equations, you can get, or you can find the values of current and value of each potential at each point. Okay. Then moving on to the second law, that is Kirchhoff's current law. And in this law, here the 3 points, that is introduction of the law, nodes analysis and exercise. The first one involves mesh analysis, whereas in this nodes analysis. So let's see what is this Kirchhoff's current law. Kirchhoff's current law is sometimes called as Kirchhoff's first law. Kirchhoff's current law can be known as first law of Kirchhoff's, and this is also known as Kirchhoff's junction rule, because it is applicable to the points of junctions. Hence it is named as junction rule also. So here in this lesson, it will be shown how Kirchhoff's current law describes the current flow through a junction of a circuit. So here, what does this Kirchhoff's current law helps us to know is how the current is flowing through a junction. It's not through the total loop. It's through a junction. How the flow of current takes place can be known with the help of Kirchhoff's current law. And along with that, Kirchhoff's voltage law also makes up the two fundamental laws of electrical engineering. This Kirchhoff's current law and voltage law are the two fundamental laws of electrical engineering. Okay. Kirchhoff's current law helps to solve unknowns when working with electrical circuit. What's the use of knowing about Kirchhoff's current law is it helps to solve the unknowns, means to find out the unknown values when we are working with electrical circuits. Then next what is the other use? Kirchhoff's current law with the addition of voltage law and Ohm's law will allow the solutions of complex circuits, not only a simple electric circuit, even complex electrical circuits also can be solved using Kirchhoff's two laws and Ohm's law. As you have seen in the first one, we have applied Ohm's law and finding the potential. So with the help of these Kirchhoff two laws and Ohm's law, we can find or we can solve the complex circuits also. Now moving on to the details of Kirchhoff's current law. What is this Kirchhoff's current law? It states that a junction is any point. Before going to the current law, you must know that it is speaking about or it is describing about a junction. What it is? What is a junction? A junction is any point in a circuit where two or more circuit paths come together. Where we say is a junction is, it's a point in a circuit. So we are speaking about circuits. So a junction is a point in a circuit where two or more circuit paths are meeting together. As we move on to the roads also, at that junction we say junction means a point where the different paths are meeting at a position or at a place. That is known as a junction. In general, four roads junction we say. So here all the four roads are meeting at the point and that point is known as a junction. Hence it is four road junction. The same way in the electrical circuit also, junction is a point where two or more circuit paths come together. So if you observe closely this circuit here, this is the point where the three different paths are meeting. One from this way, other one from right side to the left and from bottom to top. So here in detailing clearly it is given here. So this junction is the point of meeting of three different paths. The same way here also. It can be two or more than that also. Now let's see the Kirchhoff's current law in detail. What does this law states? This law states that the algebraic sum of all the currents entering and leaving at any point in a circuit must be equal to 0. I repeat it again. The algebraic sum of all currents entering and leaving any point in a circuit must be equal to 0. So this law states that the algebraic sum of currents. So when we say that algebraic sum means it includes the sign conventions are also taken here. So the algebraic sum of currents entering are taken as positive and the currents which are leaving are taken as negative. So these currents which are entering or leaving at any point and that point is junction. So this algebraic sum of all the currents entering and leaving must be equal to 0. This is known as Kirchhoff's current law. Now see this junction here. So here in this junction, when you take this as a junction, the path which are meeting, four paths are meeting at this point and the directions of current is different. So this is moving into the junction whereas this current is moving away, means leaving the junction. So this is negative whereas this current is moving into the junction, so it is positive, and this current is moving away from the junction, which is taken as negative. So here I2 is moving into the junction, so it is positive. I1 is moving away, it is negative. And I4 is also moving away, it is negative. I3 is moving inside, so it is positive. But the algebraic sum of all these currents is equal to 0. This is known as Kirchhoff's current law. What is Kirchhoff's current law? The algebraic sum of all the currents entering and leaving at a junction in a circuit is equal to 0. It is restated as the sum of the currents into a junction is equal to the sum of currents out of the junction. So it can also be stated as the sum of the currents entering into a junction is equal to the sum of the currents leaving the junction. See here, the algebraic sum of all the currents entering are taken as positive and which are leaving are taken as negative. Now if you see this junction here, I1 is entering, so it is positive. I2 is also entering, it is also positive. I3 entering, so it is positive. And I4 and I5 are leaving the junction, so they are negative currents. So this Kirchhoff's law is explained in detail here. Currents entering the node equals to the currents leaving the node. Node means here the junction, it means the same. So the currents which are entering the junction are equal to the currents leaving the junction, which means that here in this junction I1, I2, I3 are entering, so they are positive. And the junction which is leaving is the currents which are leaving are I4 and I5. So they are considered as negative, minus and minus I5. But the algebraic sum of them is equal to 0. So here the three currents entering the node are positive and the two currents that are leaving the node are negative. And in an equation it is represented as I1 plus I2 plus I3 minus I4 minus I5 is equal to 0. Okay. Now next step is nodes analysis. What is this nodes analysis and what is the use of it? Analysis using KCL, that is Kirchhoff's current law, helps us to solve for voltages. So the Kirchhoff's current law helps us to solve voltage, means helps us to calculate the voltage at each common node, means it is at each common junction of the network we can calculate voltage. So in a circuit, when you have to find out the voltage at any point can be done using the second law, that is Kirchhoff's current law. Now time for nodes analysis procedure. What it is? That is how the nodes analysis can be done. The steps are as follows. First thing, you have to find out the common node, means that is the common junction for the network. Determine the number of common nodes and the reference node within the network. You have to first find out the common node and the reference node within the network. So for a network, how many common nodes are present? And connecting to that common node, how many reference nodes are present also you have to first determine. Then assign the direction of current to it, to each branch, means to each path of the node and in the network. Then to that you have to apply KCL, means applying Kirchhoff's current law. So when you are applying Kirchhoff's current law for each junction, you will be getting an equation. So when you solve the when you solve those equations, you will be getting the values of the current and the voltage which has to be found out in the network. Solving the next step is solving the resulting simultaneous linear equations for the node voltage. Then determine the currents through which are passing and voltages across each elements in the network. So these are the steps in analyzing nodes. So what are the steps in the nodes analysis? First step is identifying the common node. The next step is to assign current direction to it. Then apply Kirchhoff's current law. Then solve the equations. After solving the equations, find out the values of I and V. Okay, let's apply now. Now let's apply the knowledge of Kirchhoff's current law in solving this problem. See the question. Find the current flow through each resistor using node analysis for the circuit below. So here you have to find out the current flow through each resistor. Here three resistors are connected. So for each resistor you have to find out the amount of current flow using node analysis procedure. Let's apply Kirchhoff's nodes analysis in solving this problem. The steps involved in this are three. The first step is finding out the common node and reference node within the network. So here, when this is the network, the common node is the point which is meeting. The paths which are meeting is known as the common node. So VA is the common node and its reference node is C. Then second step is assign current and its direction to each distinct branch of the node in the network. So here second step is to assign the direction of current for each branch of the node. So here there are three branches. This is the first one, second one, and this is the third one, third branch. So here the direction of the current for the first branch is positive because it is moving towards the junction. Similarly, the second one also is moving towards the junction. So here the current direction is positive. And the third node is moving away from the junction. So it is negative here. Then third step is apply KCL, Kirchhoff's current law. That is what it is, sum of the currents entering is equal to the sum of the currents leaving, which means that I1 plus I2 is equal to I3. Now let's see what are these values. We know that using Ohm's law, V is equal to IR, I is equal to V by R, and the value of V for the first part is 10 minus VA because the potential here it is V. Voltage is 10 volts here and it is traveling towards the VA. So here the voltage at this point is equal to, for this path is equal to 10 minus VA by 10 ohms. Similarly for the second path, the potential here it is 20 and for this path the voltage is equal to 20 minus VA by resistance is 20. So 20 minus VA by 20 is the I2 value and I3 is equal to amount of current which is flowing is we don't know, so that is considered as VA. So VA by 40 is equal to I3. Now applying Kirchhoff's current law to it. It states that I1 plus I2 is equal to I3. Substitute the values of I1, I2 and I3 in this equation. Then we'll get that 10 minus VA by 10 plus 20 minus VA by 20, that is I2, is equal to VA by 40. Now by solving this equation 10 by 10 we'll get 1. So 1 minus VA by 10 plus 20 by 20 is equal to 1 minus plus into minus is minus. So minus VA by 20 is equal to, it is VA by 40 on the right hand side. Now when you add these two equations, when you add or solve this equation, we'll get that 1 plus 1 is equal to 2 and here we have VA by 10, VA by 20 and on the right side we have VA by 40. So taking all these values to the right side, we'll get that VA by 40 is equal VA by 40 plus VA by 10, because when we take the negative term to the right side, to the other end of the equation, crossing the equal to, it becomes positive. So minus VA by 10 changes to plus VA by 10. Similarly, minus VA by 20 changes to plus VA by 20. So the equation transforms as VA by 40 plus VA by 10 plus VA by 20 is equal to 1 plus 1 we have already have 2 here. And taking out VA common from this equation, we get that VA into 1 by 40 plus 1 by 10 plus 1 by 20 is equal to 2. And here these are the fractions, three different fractions, and you know the calculation of it, the LCM is 40. So its numerator will be the same, 1 plus, when you read 10, here 10 fours are 40. So 1 plus 4 is 5. And when you add this fraction 20, it is 20 twos are 40. So 2 into 1 is 2. So here when you add to this two fractions, it becomes 7 by 40. VA into 7 by 40 is equal to 2. And from this equation, VA is equal to, when you solve this, 2 into 40 by 7, which on solving you'll get the value as 11.428 volts. And when you substitute this VA in this equation, in this each term, I1 is equal to, we know that 10 minus VA by 10. On solving, we'll get that I1 is equal to minus 0.1143 amperes. Similarly, I2 is equal to 0.429 amperes and I3 is equal to 0.286 amperes. Thus, we have got the values of current for each node in the network. So, in this way, Kirchhoff's current law is helpful in finding the values of current. Now, let's see how far you have understood this topic. Kirchhoff's first law states that current loses strength as it flows about a circuit. Are you all ready? Okay. Now let's see. I repeat the question. Kirchhoff's first law says that current loses strength as it flows about a circuit. Second option, voltage loses strength as it flows about a circuit. Third one, wires need insulation to stop electrons from leaking out of the wire. All these are not related to the Kirchhoff's law, I think. So the next option is total current flowing into a point is the same as the current flowing out of the point. I think this is connected to the first law, is it not? So the option is D. So Kirchhoff's first law says that total current flowing into a point is same as the current flowing out of the point. That is, current entering into the point is equal to the current leaving the point. Now the second one. Kirchhoff's current law is used when solving circuits with which one? Closed loops, sufficient nodes or junctions, capacitors, or none. I think the answer is closed loop. Is it not? Kirchhoff's current law is applicable for closed loops. Now the third one, nodal analysis applies the following principles. Node analysis, where we are applying for the Kirchhoff's voltage law or Kirchhoff's current law. So answer is the second option, B. Which of the following statements is true? Mesh analysis is easiest when a circuit has more than two nodes. Next option, mesh analysis is more difficult than nodal analysis. Nowhere it is connected to the laws, Kirchhoff's laws, because whether it is single node or more than two nodes, we can calculate. Mesh analysis employs Kirchhoff's voltage law to solve loop currents. Then, next question. If a circuit contains three loops, how many independent equations can be obtained with Kirchhoff's second law? How many equations can be obtained, ma? If there is a single loop, single equation. Two loops, two equations. If there are three loops, then three equations. See the last question now. How much is current I3 in the node shown? So here, it is a node of three branches with current I1, I2 and I3. I1 and I2 are leaving, whereas I3 is entering into the junction. So here, as per Kirchhoff's current law, we know that sum of the currents entering is equal to the sum of the currents leaving. Leaving currents are 3 amperes and 5 amperes. So their sum is equal to 8. 3 plus 5, 8 amperes. And this should be equal to the current which is entering. So I3 should be equal to the value of 8. So I3 is equal to 8 amperes. So with this, I'll close the session and I want you to complete the worksheet which is given to you. Okay, thank you. Next one. How much is current I4 in the node shown? So this is another node which represents that there are 4 branches are present and I1 is entering, I4 is leaving, I3 is also entering. So first you have to identify entering nodes. What are the entering nodes? I1 and I2 are entering. Sum of them is equal to 8 amperes. The leaving nodes are I4 and I3. I3, so sum of entering nodes is equal to sum of the leaving nodes. So here entering nodes are 8 amperes. Leaving nodes is equal to 10 plus I4. I4 value we don't know. But the sum of them should be equal to 8. So what should be the answer? When we'll get 8, so when you subtract 2 from 10, then we'll be getting 8. So the answer is minus 2 amperes.